Welcome back to this module on synchronization in shared memory systems. In this lesson I will present some other atomic read, modify, write instructions beside test and set, in particular the load linked and store conditional instructions. Besides test and set, there are many other atomic read, modify, write instructions. On this slide I will discuss a few of them. The first is called atomic exchange. It exchanges a value in a register for a value in memory. Here's an example: exchange R1 log. This instruction reads the log variable from memory into a temporary storage T, writes the contents of register R1 to the log variable, and then copies the temporary storage T to register R1. All of this is done automatically, indivisibly, as indicated by the circled plus symbols. Another atomic read, modify, write instruction is fetch and increment. This instruction reads the log variable from memory and increments the log variable. Here's an example. Fetch f&i R1 log. As said, it reads the log into register R1 and increments the log. Fetch and increment is said to be useful for implementing circular buffers, for example. The final read, modify, write instruction I would like to discuss is not a single instruction, but a pair of instructions: load linked and store conditional. These synchronization primitives require a bit longer explanation. The problem with conventional atomic read, modify, write instructions is that they require a read and a write in a single instruction that cannot be interrupted. This does not fit well with pipelined execution, since they require the atomic execution of two memory accesses, a load and a store. One way to solve this problem is to provide a pair of instructions, a separate read and a write, plus a way of deducing if the pair was executed atomically. This is the idea behind the load linked and the store conditional instructions. It starts with a load linked, sometimes also called load locked instruction. This instruction loads the log variable from memory just as a normal load instruction. Somewhere, however, it is noted that a load linked instruction was executed. Sometimes shortly after the load linked, a store conditional instruction is executed. The semantics of these instructions are the following. If no other thread has written the log variable since the previous load linked was executed, register R2 is written to the log variable and R2 is set to 1, indicating that the store conditional was successful. Otherwise, there was a nasty other thread that had written the log variable and R2 is set to 0, indicating that the store conditional failed. The beauty and also the power of the load linked and store conditional instruction is that any other atomic read, modify, write instruction can be easily implemented using LL and SC. For this reason, all modern multicores support the load linked and store conditional instructions. To illustrate this, let's implement fetch and increment using LL and SC. First, we load the log variable to be incremented into a register R2 using load linked. Then we increment R2 with 1 and store the result in another register R3. Then we try to store the incremented value in R3 using store conditional. If we succeeded, meaning no other thread has written the log variable since the load linked, 1 will be returned in R3. Otherwise, 0 will be returned. Finally, we test if the store conditional succeeded. If not, we branch back. If yes, we're done and successfully incremented the log variable. I now very briefly discuss how load linked and store conditional can be implemented in hardware. When the cores are interconnected by a bus, the bus interface can support a load link bit and a link register as shown here on the top right. When a load linked instruction is executed, the LL bit is set and the address of the value loaded is copied to the link register. Thereafter, the bus interface snoops, monitors all update or invalidate coherence requests. Recall that any write must be broadcasted on the bus. Then, if the address broadcasted on the bus matches the address in the link register, the LL bit is cleared. Finally, when the store conditional is executed, the LL bit is tested. If it is still set, there has been no write to it since the previous load linked and the store conditional succeeds. If not, if the LL bit is cleared, the store conditional returns failure. To be 100% correct, we also need to clear the LL bit when the lock variable is evicted from the cache and on context switches, since then we no longer keep track of other writes. Finally, I remark that there can be multiple LL bits and link registers for different addresses, so several locks can be supported simultaneously. Finally, I will sketch how the acquire operation of a spin lock can be implemented using load linked and store conditional. It is in fact very similar to the implementation of the acquire operation using test and set. First, we load the lock variable into a register R2 using load linked. If the lock was already set, we repeat. If not, we first write the value 1 into a register and then try to store the value 1 into the lock variable using store conditional. If not successful because there was another store in between the branch in between, then we branch back to the beginning. Otherwise, we successfully acquired the lock and can return to the calling thread. So what's the advantage of this implementation over the implementation based on test and set shown on slide 9? In fact, the implementation using test and set was shorter and somewhat simpler. But the advantage is that the load linked does not need to be treated as a store and therefore doesn't require invalidations. This implies that a processor can spin on its own cached copy of the lock variable until the thread holding the lock releases it. In other words, this implementation automatically provides the same advantages as the test and set implementation. Finally, a pair of questions that might be asked during a final test. The first is a simple knowledge question. The second is a short coding question. Implement the atomic exchange instruction using load linked and store conditional. This completes this lesson. Thanks for watching this video. In the next lesson, I will explain the basics of memory consistency, which is a difficult topic which defines the orders of reads and writes, loads and stores to different addresses. We might have to reconsider everything we learned about that in single core technology. Hope to see you back.